rate of change. The average rate of change will always approximate the instantaneous rate of change, but by using the limit process, we can actually get at the instantaneous rate of change. So I showed this in class, but I'm just going to go over it again. So the idea is we create a second point. If we're trying to find the derivative at, or I'm sorry, if we're trying to find the instantaneous rate of change at x, then we create this other point called x plus h, which is just h away from x. And then that produces this point q. So basically what we're going to do is just find the slope of the line through P and Q. So that would look like this. And of course the slope of that line is not the same as the slope at P, which looks like this little black line. So but what we would say is that it's a decent approximation. Right now it's way off. But if we let h get smaller, then we can see that as h gets smaller, which means x and x plus h get closer and closer together, the green line gets closer and closer to the same slope as the black line. So therefore, as we let h get ever increasingly small, the average rate of change, or the average slope, is going to get closer and closer to the instantaneous slope at that point, and the instantaneous slope is what we're interested in. Okay. So that's just a reminder of what we talked about, and stop that, close that. So if we're looking at an equation like, for example, f of x equals x squared, we all know what that thing looks like. It's a parabola, something like this, right? And let's say we want to know the slope right there at the point 1, 1. Well, we could pick another point like right here, and we could say that the slope of that line is going to be f of 2 minus f of 1 over 2 minus 1. And of course, f of 2 is just 4, so that would be 4, and f of 1 is 1, because it's just 1 squared, so that'd be 1. So we get 4 minus 1 over 2 minus 1, that would be what? 3 over 1. So the slope of this thing, of this line, is 3. But that's not what we're looking for. We're looking for the instantaneous slope at this point. So the idea is we want the point, we want the point 2, 4 to get closer and closer to 1, 1. So what we're going to do is we're going to take f of 2 plus a little bit minus f of 2. And then on the bottom, we're going to put 2 plus a little bit minus 2. And that would be the average rate of change for a point. And now it's just some undisclosed point. So we don't know exactly where it's at, but it's somewhere out here. Where, I'm sorry, I don't know why I put 2. That should be 1. My bad. Let me do that over again. Because I'm trying to find the point right here, aren't I? So that should have been 1 plus h. That would just be 1. It's be 1 plus h minus 1. Because I'm trying to find the instantaneous rate, or the instantaneous slope at this point right here. Okay? So, so again, this point right here would be the point 1 plus h, comma, f of 1 plus h. So we're just finding the slope of that line again. And we could do this a bunch of times, making h smaller each time. But a way to do that really quickly is we throw the limit out in front and let h approach 0. And this, so without the limit, when it's just like that, that's an average rate of change. When I throw the limit in front of it and let h approach 0, if we can evaluate that limit, that will give us the instantaneous rate of change. And the instantaneous rate of change is what we call the derivative. So this expression right here is called the difference quotient, but when we put a limit in front of it, this is what we call the definition of derivative. This is how a derivative is defined. It's the limit of the slope of the secant line as the distance between the 2 points gets smaller and smaller. And that's what we're doing here. So in this case, we would say that the limit as h approaches 0 of 1 plus, 1 plus h squared minus 1 squared all over. Now 1 plus h minus 1 would just be h, wouldn't it? So then that would be the limit as h approaches 0 of, well, that'd be 1 plus, if we square this, that'd be 1 plus h times 1 plus h. That would give us 1 plus 2h plus h squared minus 1 all over h. And of course, 1 minus 1 is 0. So that would leave us with limit as h approaches 0 of 2h plus h squared all over h. And since h is a factor of the top and bottom, we can reduce that to 2 plus h over 1. So now we can try to evaluate this limit as h gets close to 0. 2 plus h is going to get close to 2. So that means the slope of the tangent, or I'm sorry, the instantaneous slope at this point would be 2 over 1. Okay? Now let's say that we wanted to just get a generic expression. In other words, this tells us what the slope is at instantaneous slope at that point, and we know the slope is different at every point. So if we wanted to find out maybe an equation for finding the slope at any point on this graph, then we could start out once again with f of x equals x squared. And once again, we'd say, let's take the limit as h approaches 0 of f of x plus h minus f of x. So instead of putting in a 1 for x, we're just leaving it as x. And this would be x plus h minus x. So once again, if we have that picture, so we've got this, let me blow it up a little bit. We've got this stretch of the parabola, right? This could be any point on the parabola. We could pick a point right here, and we'll call that x, comma, f of x. And there'll be some other point, and that will be x plus h, comma, f of x plus h. So those are my 2 points. We can draw a secant line through that, and we want to know what the actual slope is at that point. So you can see this line up here, the highlighted in blue, in green. So that green line is the secant line, and this pink line is the actual, we call it the tangent line, which represents the slope at that point. Okay? So, and of course, like we said, as h approaches 0, if we take the limit as h approaches 0, this green line approaches the pink line, and the slope of the pink line is what we want. So in this case, since f of x is x squared, we're going to write this as limit as h approaches 0 of x plus h squared minus x squared. Of course, x plus h minus x is just h. And if we take the limit, or we keep the limit because we haven't taken it yet, so if we multiply that out, x plus h times x plus h, that would be x squared plus 2xh plus h squared minus x squared all over h. And just like the ones disappeared before, we have an x squared here and a minus x squared there, so those will disappear because they add together to get 0. And so then we're left with 2xh plus h squared all over h. H is once again a factor of the top and bottom, so that becomes the limit as h approaches 0 of 2x plus h, because the other h's canceled out. And when h gets close to 0, this overall expression gets closer and closer to 2x. So that tells me that if I wanted to know what the slope was of x squared at any point, 2x would tell me the answer. So 2x is a formula for finding the derivative of f of x. And now, just to give you a little notation, we write that as f prime of x. That's one way to write the derivative. So we're saying if f of x is x squared, that means f prime of x is equal to 2x. Another way to write the derivative is dy dx. So these two are two ways to write the same thing. Okay? So that means if I want to know what's the slope of this parabola when x is equal to 3, I can just plug a 3 in here and I get f prime of 3, which would be equal to 6. So when at the point 3, 9 on this graph, the slope, the instantaneous slope, is 6, or 6 over 1. Okay, so let me do one more example. Let's say the function is f of x equals the square root of x. And I want to find the slope, the instantaneous slope, a formula for the instantaneous slope. So that would be the limit as, so I plug into that same thing I did before. I'm going to take a, as h approaches 0, I'm going to pick two x values, like x plus h minus x, right? So that means up here I'm going to have x plus h plugged into the formula for the function, and just x plugged in. So you can see that should look similar to the one we started with up here, right? Where in this case it's squared and squared because our formula for the function was x squared. Down here we have square root and square root because the formula for the function is square root. Okay, so if we go to simplify that, there's not a lot I can do except for x minus x is 0, so that's just h. And now up here we got a problem because if I let h approach 0, the bottom approaches 0, and then I don't know I can't evaluate that. So I need to somehow deal with that. Now, if you've already watched the earlier evaluating limits video, you know when we have square roots in the top of the fraction, we can use this little technique called rationalizing the numerator. And so what that looks like is you multiply by the square root of x plus h plus the square root of x, both top and bottom, so that makes it legal because I'm multiplying top and bottom by the same thing, which is just like multiplying by 1. And so what happens is we get the limit as h approaches 0. And of course, this is a distributive property thing, right? So multiply this times this, and that gives me x plus h. And if we multiply the inside times the inside and the outside times the outside, notice you get the same thing, only opposite. So those cancel each other out. And then finally we multiply the negative square root of x times square root of x, and that gives me negative x. That's on top, and on the bottom I have this whole spiely. And something cool happens. The x and the negative x, of course, add together to be 0. So I'm left with just an h on top. So that'd be a limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. Of course, the h's cancel out, and I'm left with the limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. And now I'm ready to let h approach 0 again and see if this thing works out better. So as h approaches 0, this expression right here gets closer and closer to just the square root of x. So that means this limit is going to approach 1 on top, and the bottom looks like it'll just be 2 times the square root of x. Because as h gets closer to 0, this expression gets closer and closer to the square root of x, which means this overall expression gets closer and closer to 2 square roots of x. So once again, if your function is the square root of x, then the derivative of that function is 1 over 2 times the square root of x. What is the derivative? It's the instantaneous rate of change. If we're thinking in terms of a graph, that means it's just the slope, instantaneous slope. If we're talking in terms of the context of the problem, whatever the function is, f prime of x would be the instantaneous rate of change of that function. All right, so that's a little spilly on finding the instantaneous rate of change using the limit process, or otherwise known as the definition of derivative.